Hey Chem 100, this is Dr. Ricardo. This is our fourth video in Chapter 9, which is on stoichiometry. So we're picking up on page 13 of the notes. We skipped a few pages where I did a demonstration with nuts and bolts that I usually do in class that tries to explain why understanding the limiting reagent concept is so important. So I replaced that in the video with a Legos demonstration. So this video follows the Lego demonstration of the limiting reagent questions. All right, so this question is called a mass to moles question because they ask you how many moles of iron oxide can be obtained by reacting 16.8 grams of iron. So they give you the mass of iron and the mass of water, and they want to know how many moles of this particular form of iron oxide, which is called ferrite, you can make. Okay, so the overall balanced equation is given to you. So if we started to mark this chemical equation up, I start with 10 grams. I usually would write 10 grams over here because that's the amount of iron that I start with. 16.8 over here, and then 10 grams over here. Okay, so those are the two starting materials. Those are what are going in. Now, as soon as I see two masses on the left, I have to say to myself, wow, I don't know which of these two things I'm going to run out of first. So this is a limiting reagent question. We are going to run out of one of them. We don't know which one first. Once we run out of that material, we're going to wind up with leftover of the other pile. Maybe it's leftover iron, or maybe it's leftover water. What's the product that we want to find out about? We want to find out about this material. Okay, so that's what they're asking us about. So I put a question, and in this case, I want to know how much I can make in moles. So I don't have to go all the way to grams. I can stop at moles. Okay, so I'm going to need two molar masses. So I'll do those two over here. The first one is water, which we've done many times. Water is 18 grams per mole. We're going to need that, right? And that's from oxygen being 16 grams per mole and each hydrogen being 1. So 16 plus 2 gives you 18. And then we need the molar mass of elemental iron, which we can get right off the periodic table. So if you grab your periodic table, iron is right here. It's 55.84. So you can round that to 55.8. So that's the number that we're going to use. Actually, I use 55.9 on here, so I'll go ahead and use 55.9 on here. Okay, so first thing we're going to do is take the grams of iron, work it all the way through to moles of the ferrite, and see how much we get. Then we're going to do a parallel calculation with the 10 grams of water. We're going to get two answers. The answer that's lower is going to be the correct answer, and we're going to throw out the higher one. So we start out with our 16.8 grams of iron right from the question. I divide by 55.9 because that gives me right there, if I stopped at that step, that would give me the number of moles of iron that I have. So first step, you can only do stoichiometry. You can only relate things when they're in moles. So the first step is always to get to moles from grams. How do you do that? Divide by the molar mass. The next step, if I would get off the superhighway right there, it turns out that 16.8 divided by 55.9 gives you exactly 0.3 of this material. Okay, just a coincidence that it's a round number. The next step that I'm going to do is I'm going to relate the coefficients. How many moles, can't say how many grams of this are related to how many grams of this, but I can say how many moles of iron are needed to create 1 mole of the ferrite. So that relationship is 3 to 1. 3 go in, 1 come out. That's why the 3 goes in the denominator. Once I get to that step, I'm done because this particular question asked me for moles of ferrite, and that's what I have. Grams would cancel here, moles of iron would cancel here, and moles of the product would be left. So 16.8 divided by 55.9, put it into your calculator, get 0.3. 0.3 divided by 3 gives you 0.1. Again, just a coincidence that you get a round number. So you're able to create 0.1 moles of the product that we're interested in if all 16.8 grams of the iron were to react. But we don't know if that's the case yet. we have to compare that with the same calculation for water. Take my 10 grams of water, which comes right out of the question, divided by 18. Where's the 18? That's the molar mass. Right now I'm in moles. 10 divided by 18 gives me 0.55. So I'm able to make 0.55, not able to make, I have 0.55 moles of water whenever I have 10 grams of water. Let's make this decimal point a little better. Okay, and so with this one too. Good, all right. So the next thing I have to do when I'm in moles is I need to compare this coefficient with this coefficient. For every 4 water molecules that go in, only 1 ferrite come out. That's why the 4 is in the denominator and the 1 is in the numerator. Look back over here. When we were comparing iron to ferrite, it was a 3-to-1 ratio. We put the coefficient of the material that we have already in the denominator and the coefficient of what we're interested in the numerator. So that's why this one is 1 mole here and 4 moles here from this 4-to-1 relationship. Okay, go through, do the math. 10 divided by 18 gives you 0.55. Divide that by 4, you get 0.139 moles of iron oxide. When I have to compare these two, I see this number is bigger than this number, therefore I cross this out. This never happened way back after I formed 0.1 moles of iron oxide. I wasn't able to make the rest here because I ran out of this material first. So the second part of the question, which substance is the limiting reactant? The substance that gives you the correct answer, the substance that gives you the smaller answer, is the limiting reagent. I ran out of iron first. This reaction came to a grinding halt when I ran out of my 16.8 grams of oxygen. There was still some excess water left that didn't completely react when this reaction ended. Okay? Good. So that's the foolproof method. When you have a stoichiometry, you take them soup to nuts. From the 2 materials that you start with, go all the way to the product, compare the 2 numbers. The smaller number is always the correct answer. If you had 3 different reactants, X plus Y plus Z, you go through this analysis 3 times, you get 3 numbers, still take the smallest number, throw the other 2 out. Okay? So the limiting reagent is iron. We determined that because iron gave us the correct amount of product that we could form. And it determines the amount of product. So the limiting reactant or the limiting reagent is the reagent that you run out of first. The maximum amount of iron oxide that can be formed is 0.1 moles. Okay. So that's the first way of thinking about it. The next way of thinking about it is to go back and take our balanced chemical equation. Let me just erase these guys here because I'm going to need them for the next time. Take our balanced chemical equation and let's tabulate in moles how much of everything I have, how much it changes, okay, how much it changes, and what do I have at the end. So I can put these coefficients in front of this here so that I can see everything in one place. So this was a 3 plus a 4 reacts to make a 1 plus a 4. Okay? So those are the coefficients here. They came right from above. Okay? All right, so first thing we want to do is how much do we have when we start with? You need to do this in moles because only moles can be related in an accounting fashion like this. You can't do this, it won't work if you put the numbers in directly in grams. So where did we get this 0.3 and this 0.55 from? We got that, same as we did up here, just by taking the initial amount of iron from the question, divide by its molar mass to get the 0.3. So that's how much we have at the beginning of the reaction. How much water? Same as we got over here, 10 grams divided by its molar mass gives us 0.55. How much of these 2 products do we have? None. We didn't make any yet. The chemistry didn't start. Okay, so we're tabulating how much we have before the chemical reaction starts, how much it changes by, And what do we have at the end? Okay, so follow this logic. We know this reaction has to go to the right. These two things are present. They want to react with each other. Put them together, they will react with each other. We'll follow the stoichiometry. For every 3 of these that I use up, okay, that's 0.3. I'm going to use them all up because it's the limiting reagent. How much of this do I use up? Well, if I use up 3 of these, look at the relationship. This is a 3 to 4 relationship. Every time I use 3 of these, I use 4 of these. So if this goes down by 0.3, this goes down by 0.4. A 3 to 4 relationship is the same as a 0.3 to a 0.4 relationship. Okay, follow the logic for the other side. For each 0.3 that reacts over here, that this goes down by 0.3, this goes up by 0.1. Why up? Because it's a product. And why 0.1? Because for every 3 of these that I start with, I'm only able to create 1 of these. So this goes down by 0.3, this goes up by 0.1. Okay, let's take a look at the hydrogen. We're right there, right? Well, I don't have any to start with. For every 4 of these that go down, 0.4, 0.4 of these must grow in. Look at that. This guy has a coefficient of 4. This guy has a coefficient of 4. It's being used up because it's a reactant. It's being created because it's a product. If I take the before line and I subtract off how much it changes by, I get how much I have at the end. I start with 0.3. I use every single bit of it up. I run out of it, so it goes down to 0. The thing that I run out of first is called the limiting reactant, so I circle that. Okay? All right. This line here has to follow the coefficients. 0.3 to 0.4 is the same as 3 to 4. 0.3 to 0.1 is the same as 3 to 1. We did this analysis. 0.4 to 0.4 is 4 to 4. 1 of these grows in while 4 of these grow in. That's why this one is 4 times bigger than this one. So these numbers here, just a coincidence that they're so nicely related. They're 1/10 of everything. But no matter what question you do, these will change with the same relationship as these coefficients. That's something you can look for. Okay, how do I get the last column? I just do the subtraction. 0.3 minus 0.3 equals 0. 0.55, the amount that I started with in the beaker, goes down by 0.4, so what's left? 0.15, just subtract. Started with 0, go up by 0.1, my ending amount is going to be 0.1. Start at 0, go up by 0.4, my ending amount is going to be 0.4. Okay, so this is the thing that we were asked to calculate right here. It's just another way of doing it. What's nice about doing it with a mole table like this, where you look at how much you have before it reacts, how much it changes by, and how much you have after it reacts, is basically it's like an accounting mechanism. You keep track of everything that you have, and you get some ancillary answers too. Like for instance, someone might ask you, well, okay, if this was the limiting reagent and it goes down to 0, how much water is left over? Well, look how easily this table gives you that, right? You just take the difference and that's how much is left over. Good? Again, it's got to be in moles. Okay, here's a second example. How many grams of silver bromide, AgBr, can be formed when solutions containing 50 grams of magnesium bromide and 100 grams of silver nitrate are mixed together? So this is a double replacement reaction. It's given to you balanced. 2 MgBr2 aqueous react with 2 AgNO3 aqueous to make 2 AgBrs and 1 MgNO3. Okay? This guy here, the little line going down, we would usually write it as solid, right? You're making this thing, it's a solid. The line going down means it forms a precipitate. Okay? Okay. If, not going to do it this time, but if I had to do it, the molar mass of magnesium bromide is 184.1. I'm going to give that to you so we can get on with the harder stuff. The molar mass of silver nitrate is 169.9. The molar mass of silver bromide is 187.8. Okay, and nobody asked you about magnesium nitrate because it's still in solution, so I didn't bother calculating it. Where do I get these numbers? Right from the periodic table. Okay, so let's take a look at our first foolproof method. So the foolproof method is to do this twice. First, assume that it's the 50 grams of magnesium bromide that you're going to run out with. Take it all the way to the answer. Then do the calculation with the 100 grams of silver nitrate that you start with. Take it all the way to the answer and see what you get. Okay? So here we go. I have 50 grams of magnesium bromide. That comes right from the question. First thing, you cannot do stoichiometry in grams. You have to change to moles. So how do we get to moles? We divide by the molar mass, the 184.1. Okay? So that looks like that. If I would get off the superhighway right there, 50 divided by 184.1 would give me 0.27 moles of magnesium bromide. But I'm not going to get off. I'm going to keep going. Next step. Once I'm in, grams cancel out. Once I'm in moles of magnesium bromide, I look at the balanced equation. That's always the step in the middle. First step, divide by the molar mass. Step in the middle, multiply by the coefficients, okay, or use the ratio of the coefficients. For every 1 magnesium bromide that I start with, I'm able to produce 2 of the product. I get twice as much product. That's why it's a 2-to-1 relationship. This 2 here comes from there. This 1 comes from there. It's not just because it's a reactant, it's because it's the thing that I have. I put the thing that I have in the denominator and the thing that I'm interested in getting in the numerator. Right? Don't have to do anything with this or anything with this one at this point. Okay, when I get to that step, right there, I could get off like I did in the last question, and that would give me moles of silver bromide, the substance I'm interested in. I would take 50, divide it by 184.1, then multiply by 2. But I want to keep going. I want to go all the way to grams because the question said, how many grams of silver bromide can I form? So what do? Last step, multiply by the molar mass of the thing that you're interested in. The one you wanted to get rid of, 184.1 goes here in the denominator. The one you want to get to goes here in the numerator. Moles of silver bromide cancel with moles of silver bromide, and I'm left with grams of silver bromide. Okay, do the math. 50 divided by 184.1, get the answer. Times 2, hit equals, times 187.8, my answer would come out to 102. Why just 3 significant figures? This one in here had 3, even though these are perfect. This is a perfect relationship of 1 to 2, okay, or exact relationship. And this is higher than 3 significant digits, and this is higher than 3 significant digits, so this is the driver. Usually, the how accurately you know the starting material determines how much you can get the product to. Okay, let's go through the parallel calculation as though it's the silver nitrate that I run out of. So first step, just like I did here, divide by its molar mass. So this time I'm relating this to this. So it's going to be a 2-to-2 relationship, but before I get to that, I have to get out of grams and into moles. I always do that by dividing by the molar mass. So where's this 169 comes from? Right from the periodic table. Look up silver plus 1 times nitrogen and 3 times oxygen. You should get that number. Okay, next step, right here. Grams cancel with grams. I'm in moles of silver nitrate. Okay, the next step is the relationship here. For every 2 moles of silver nitrate that go in, 2 moles of silver bromide come out. 2-to-2 relationship. Yes, you could make it 1-to-1, but leave it. This way we can see where you got them from. This 2 and this 2. Okay, last step, right now. Moles of silver nitrate would cancel with moles of silver nitrate. I'd be left with moles of silver bromide. I want grams of silver bromide. That's what they're asking in the question. How many grams of silver bromide do I have? So, voila, multiply by the molar mass of the thing I'm interested in. Every 1 mole of silver bromide, just like the top. The last part will be just like the top. Okay? I get 110.5 as my answer. 2 answers. This one could never happen. Shouldn't have put a box around it. This one can never happen. Why? Because back at 102 grams of silver bromide, I ran out of the magnesium bromide. So magnesium bromide is the limiting reagent. Okay? If we wanted to check and think about it in terms, we don't have to, but if I wanted to check and look at it in moles, this is telling me I need twice as many moles as this. Do I have it? The answer is yes. I have more than twice as many because this amount of moles after that step comes out to 0.27. This comes out to 0.59. 0.27 times 2 is 0.54. So as long as I have more than 0.54 moles of this, the other guy is going to be the limiting reagent. Okay, that's extra, that thinking. You don't have to do that. You can just take these all the way to the answer, get the two solutions, cross out the one that's not possible because you already ran out of the other one. Okay, so let's look at the notes here, and then I'll go back and fix this up because I probably should never have put a box around that one. Okay, box kind of means it's a correct answer. So magnesium bromide is a limiting reagent, and the maximum amount of silver bromide that can be formed is 102 grams. That has a fancy name. It's called the theoretical yield. If everything went perfectly according to plan, which sometimes it doesn't, right, when you're in the lab. Sometimes you lose a little bit or something was impure, it didn't all react the way you expected. If everything worked out perfectly, you would have gotten 102 grams. The definition of the theoretical yield is the calculated amount of product that can be obtained from a given amount of reactant according to the balanced chemical equation. Calculating the theoretical yield is doing stoichiometry, is what this chapter is all about. Figuring out how much product we can make based on a given amount of reactant. So the maximum we can possibly make in a perfect situation is 102 grams. That's called the theoretical yield. Okay, if you actually go into the lab and do it, you're not going to be so lucky, right? Usually something isn't perfect. So the amount that you get when you actually do the experiment is called the actual yield. It's the amount of product obtained in an experiment. So you go in, you try it. The actual yield is going to be equal to or less than the theoretical yield. The best you could ever hope for is 102. If I went into the lab, I'd probably get 101.5 or something like that. I'm going to get some number a little bit less because it's hard to collect all the product. You could have did a little bit of spill in the beginning. Maybe the stuff isn't as pure as you thought it was. So reality isn't as perfect as the calculation. There is something that's very important called the percent yield. The percent yield is kind of how good of a job you did when you went in the lab compared to the theoretical yield. So for the percent yield, you take the actual yield divided by the theoretical yield times 100. The percent yield, for the same reason, always has to be less than or equal to 100%. The best you can hope for is perfection. If you're a baseball player and you get a hit every single time you're up, you bat 1,000, which is 100% hits. But even the greatest players, right? Even Ted Williams' best year, he batted like 408, right? So that's 4 hits out of 10 is the best that you can ever get when you really go and try to play baseball. Okay, so same thing with a test question. If there's no extra credit, the best you can ever get is 100%. So you're going to get 100% or less, right? All right, so let's look at another example. I just have to go back and just going to fix my guy up over here because I want to exaggerate the fact that I probably should not have put a box around this. So I'm going to erase the whole thing, show it to you, and then emphatically cross it out because this 110.5 never materialized because we ran out of the other guy first. So here's the foolproof method. Get the two solutions, cross out the bigger one. The bigger one in grams or moles, they're the same. Okay, they're not the same number, but whichever one is bigger in moles will also be bigger in grams because that last step, you're multiplying by the same number. Okay, one more example. Carbon tetrachloride was prepared by reacting 100 grams of carbon disulfide and 100 grams of chlorine. Calculate the percent yield if 65 grams of carbon tetrachloride, which is one of the products, that's the product that we're interested, was obtained from the reaction. Guys, we don't do anything with this 65 grams in the beginning. This 65 grams is the actual yield. It's how much you get if everything works out perfectly. Okay, well, again, things don't work out perfectly usually. When you go to try it yourself, you get a smaller number. Okay. All right, so the balanced reaction is given to you. You got CS2 plus 3 chlorines. This is carbon disulfide plus chlorine gives you carbon tetrachloride plus disulfur dichloride is the other byproduct. So put this actual yield down from the question. This is how much you got when you went in the lab and did it. So you have the numerator for this calculation. You just need to get the denominator before you can do it. How are you going to get the denominator? You're going to calculate the theoretical yield by taking each of the 2 possible limiting reagents, take them to the product, and see which one is smaller. Okay, so we're going to try this not by the table method, but by the foolproof method. So I'll start right here. Where's this 100 grams of CS2 come from? Right out of the question. I started with 100 grams of carbon disulfide. If carbon disulfide is the limiting reagent, I'm going to take that 100 grams, see how much of this thing that I'm interested in I can make. What's 76, 71, and 154? Those are the molar masses, right? Chlorine is 35.5 times 2, Cl2 would give you 71. This 76 comes from sulfur, which is 32 times 2 is your 64, plus 12 more for carbon. This 154 comes from 35.5 for each chlorine, times 4, plus the 12 for carbon. These are just calculated from the periodic table. Good. So, first step, gotta get to moles. How do I get to moles? Divide by the molar mass. That's 76 over here. So I have just a little bit more than 1 mole, right? 100 divided by 76 is something like 1.3. So if I was going to get off, I've got 1.3 moles of this. I need at least 3 times as many moles of the other guy. Okay, but we're not doing it that way. We're just going to do the foolproof method. We're just going to ram our way all the way to here, get the answers, and then check. I'm not doing anything with this guy right now. I'm just relating this to this. Okay, all right. Well, what's the stoichiometry between carbon disulfide and carbon tetrachloride? It's a 1-to-1 stoichiometry. For each mole of this, I create 1 mole of that. Well, there's how you write that down. And do write it down. Don't just skip that part. Okay? 1 mole of CS2 creates 1 mole of carbon tetrachloride. All right, if I wanted the answer in moles, I would just get off right there, but I don't. I want to know how many grams this is, right? So I'm going to multiply by my 154. Moles of carbon tetrachloride will cancel out, and I'll be left with grams of carbon tetrachloride. Okay, get the answer. 100 divided by 76. It equals times 1 divided by 1 doesn't change anything. So 100 divided by 76, then multiply by 154. I get 202 grams. Okay? Maybe that's right. We're going to see. All right, let's try our 100 grams of Cl2 again. This is 100 grams, not because it has to be. It's 100 grams because that's what they gave me in the question. They told me that I had 100 grams of chlorine, right? You don't question that. You just take what comes out of the question. That's how much you have on hand. If you were a baker, that's how much stuff you have in the cupboard. You want to figure out what you're going to run out of? Go see, take all the things down, the flour, the sugar, the eggs, the milk, put it all out on the kitchen table and say, okay, which one is in the least quantity for my balanced reaction? Okay. Let's try that. Second one. Here's my chlorine. 100 grams of chlorine. Have to divide by 71. Where does that come from? The molar mass of chlorine. 35 times 2. Right off the periodic table, 35.2 is the number for Cl. Multiply by 2 because we're dealing with Cl2. Don't do anything with this 3 yet. That's coming up now. Okay, what's the stoichiometry? For every 3 of these that go in, only 1 of these come out. That's why I have to divide by 3. 3 go in, but only 1 come out. Okay? 3 go in, but only 1 come out. So, moles of chlorine cancels out with moles of chlorine. Now I have moles of carbon tetrachloride. The last step will be exactly the same. I need 154 in the numerator because that's the molar mass of carbon tetrachloride. Moles of carbon tetrachloride will cancel out, and I'll get grams of carbon tetrachloride. Let's get the answer. 100 divided by 71, hit equals. Take that number, divide it by 3, hit equals. Multiply that number by 154. I get 72 grams of CCl4. Put a box around the correct answer. Why is this one correct? Because it's smaller than that one. Whichever one comes out smaller is going to be correct. Cross the other one out. It never happens. Way back a long time ago, almost 125 grams ago, you ran out of chlorine. So chlorine gets the special title, the limiting reagent, the substance that you run out of first. This number that gives the limiting reagent is able to create is called the theoretical yield. That's the maximum possible amount of carbon tetrachloride you can create if you start with a beaker that has 100 grams of this stuff and 100 grams of this stuff. Can't get all 200 of it to react. There's going to be leftover CS2, right? Leftover CS2. We're going to run out of this first. Okay, so let's do the theoretical yield calculation, and then we'll come back up here and see if the stoichiometry makes sense. The numbers are close, but we do run out of one before we run out of the other. Okay? So, theoretical yield is the experimental yield, which is given to you in the question, how much the scientist was able to make, 65 grams, divided by what we just calculated. You bring that down here into the denominator. Hey, there were 72.3 questions on the test. You got 65 right. What's your grade? 65 divided by 72.3 times 100. Just like a test grade. How many you got right over the total times 100. This person got an 89.9. Just barely, they got an A in class. Okay, so I think we'd be nice to them and round that up to 90. Okay, let's take a look at this and see if it makes sense. At the mole stage, okay, if you wanted to do the table, 100 divided by 76 gives you 1.3 moles of this. 100 of this divided by 71 gives you 1.4 moles of this. Okay? This one is in huge excess because I really needed, look at this, because of the stoichiometry, I really needed 3 times as much of this. Meanwhile, I don't have 3 times as much chlorine as I have CS2, right? Look, I need 3 times as many moles as this. I barely have 1. These are almost identical numbers, 1.3 and 1.4, right? In order for this one to be in excess, to not run out of it first, I would need to have more than 3 times 1.3, right? So that's 3.9, right? I don't have 3.9, I only have 1.4. So I run out of this first. It's the limiting reactant. Okay, let's do one more, and that'll be a perfect place to stop. In this reaction, silver bromide was prepared by reacting 200.0 grams of magnesium bromide and an adequate amount of silver nitrate. So adequate amount means that it's in excess. So this is going to be an easier question. We don't actually have to go all the way and do 2 separate questions and see which answer is smaller. We only have one question to do because I only have the mass, or only have the quantity of one of the reactants. Which reactant? The magnesium bromide. Okay? So we're going to see the balanced equation in a second, but this one's going to turn out to be easier. So let's read it again. Silver bromide was prepared by reacting 200 grams of magnesium bromide and an adequate amount of silver nitrate. Calculate the percent yield if 375 grams of silver bromide was isolated in the experiment. This is the actual yield. This is what you get if everything, when you really went into the lab and did it. So just put that number on the side. That's going to be our numerator in our percent yield calculation. But I can't do anything with it yet. First step, I need to calculate the theoretical yield of the product based on starting with 200 grams of the magnesium bromide reacting with another reactant that's in excess. Adequate means excess. So here's the balanced equation. Magnesium, they gave us 200 grams of this. That's my starting amount. The question is, how much silver bromide can I prepare based on my 200 grams of magnesium bromide? This guy, we had done one like this before. This guy's molar mass is 184.1. You can look it up. Look up 1 times magnesium plus 2 times bromine. Silver bromide is, look up the mass of silver plus the mass of bromine. You'll get 187.8. So these two come right from the periodic table. We're going to use them later. Okay? So this one, just for a change of pace, I might as well start it out and go all the way. Right? So I will use that there. And then underneath, I'm going to write over here, hey, this guy, I started with 200 grams. I just have it to 3 significant digits. Oh, I'm going to make it one more, right? I have 200.0. I'm going to show you the question in a second. 200.0, so I have it to 4 significant digits. Let's look up here, 200.0. And then how much of this is the stuff that I want to get out? So I can put an arrow down, question mark, and I want to know what it is in grams. So this is what's going in, 200's going in. This guy's in excess. Don't have to worry about it. I got plenty. I'm not running out of it. So the 200 grams of magnesium bromide is going to be the driver. It's going to determine how much magnesium bromide you can make. Okay. Sorry, I'm getting a junk mail call okay, or a spam call. So it'll be over in a second. Okay, should be done. All right. So, sorry, these extra 184, those are not the masses that goes in. Those are the molar masses. Okay? 200 goes in. How much of this comes out? Okay, first step. We know this is the limiting reagent because they told us the other one is in excess. I have an adequate amount. Okay? 200 grams of magnesium bromide go in, right from the question. First step. Multiply by the relationship between how many grams it takes to make a mole for magnesium bromide. So the 1 mole goes here because I want to wind up in moles. I can only do stoichiometry in moles. And what goes down here? 184.1 grams are equal to 1 mole. Okay. First step in all stoichiometry, take the mass of the stuff that you know about, divided by its molar mass right from the periodic table. This is 1 mole of MgBr2. Okay, right? Every one of these things we've been doing in the chapter, I'm taking a mass, I'm dividing it by a molar mass to get it into moles. What's in the middle? The relationship from the balanced chemical equation. For every 1 mole of these that goes in, 2 moles of those come out. So this one is an amplifier. Doesn't cut it down, it makes it more. 1 mole MgBr2 goes in, 2 moles AgBr comes out. Where does that come from? 1 to 2 relationship. This is in excess, I don't care about it, nobody asked me about this. This little arrow is the same thing as putting a solid, it precipitates. So we're going to collect this precipitate. Okay, last step. They didn't want to know the answer in moles right here. This would wind up in moles of magnesium bromide because grams would cancel out and moles of magnesium bromide cancel out. So how many moles of silver bromide? They want to get grams. 1 mole of silver bromide has 1 mass. Remember, the first on the left, you're going to be dividing by the molar mass of the old guy. On the right, you're going to be multiplying by the molar mass of the one you're interested in. In this case, that's silver bromide. So this is that. Okay? This is in the unit and the substance, silver bromide. Okay, so take my 200, divide it by 184.1, get the answer. Hit the equal sign. Times 2, hit equals, times 187.8. Do all of that. I did it down here neater. I'm going to get 408.0 grams of silver bromide. That's the theoretical yield. That's how much I could make if the chemical reaction worked perfectly. It didn't work perfectly. The person who really tried it in the lab, right, they were only able to get 375 grams of silver bromide. So that's how much they were able to make, divided by the most you could possibly make theoretically, times 100. Again, it's a test, right? There's 408 questions on the test. You get 375 right. Wow, you're pretty good. So 375 out of 408 times 100 gives you 91.9. So they did a very good job. They were able to collect 91.9 out of a maximum amount of that they could possibly collect. So 375 is very good. They only lost a little bit, right? They all lost 25 and 8 is 32, right? 33. So they did pretty well. Good? All right, so that's where we're going to stop right there. And we'll have one more video for this chapter, and we'll pick it up then.